Ciao. You're next. You want this thing?
Yeah, let's see. I think I just find this on here.
Oh, you put yours already, unless you changed it.
Oh.
If you close. Here next to mine, there's Charles.
There it goes. Just the machine. Okay, so I have a few slides.
Yours is still here.
Yeah, use this one.
Okay.
Use forward, back. The middle one is forward.
Okay. So I have a few slides on how we can explore the QCD structure of nucleon-nucleon interactions and potentially three-body interactions in tagged DIS and various variations on deep virtual exclusive scattering in light nuclei. So Orr gave us a wonderful overview of all the things we've learned and many of the questions that still remain in understanding the EMC effect. And I would say the next step is then to link this to QCD dynamics. So QCD dynamics is essentially a probe. We have deep inelastic scattering subject to higher twist corrections. It says we are looking at quartz. And we've identified the correlation between the vertical and the horizontal axes here that tells us something at the nucleon level of what's happening. But what about the dynamics, the quark-gluon dynamics of the nucleon and the nucleon-nucleon interaction? That is still not there, or still remains a great deal to explore. So a few basic facts that we know about how we can use a QCD in deep inelastic scattering. First of all, we have this what was initially sort of a phenomenological, but now these people claim is a universal understanding of an effective coupling, not just in the coupling in the perturbative regime at very high momentum scale, but all the way down to zero momentum. There's a saturation. And so, we always argue, well, how high in Q squared do you have to go? 1, 2, 4, 10. And the answer seems to be dependent upon what physics you're trying to do and what machine you have to do it with. Momentum scale of 1 GeV, or if you square that 1 GeV squared, it doesn't matter. It's, the alpha S is over pi is around 0.4. So we started to be perturbed. And then, as we, so we do our deep inelastic scattering, and the virtual photon is probing a volume whose transverse area is essentially 1 over Q squared, and longitudinal length is 1 over XM. So as we're dialing the XP arcane, we're dialing the depth in which we're probing the nucleon, or the length over which we're probing nucleon and nuclear dynamics. Oops. Master this device. Okay. So we have these horrible words called shadowing and higher twist and anti-shadowing. We had a workshop at the new center at Stony Brook talking about entanglement. And very fascinating disciplinary workshop. Unfortunately, I had to bail out after the first day because of a threat of a hurricane in Norfolk, which kind of did a circle around us and left us completely unaffected. But in any case, it was very interesting, lots of different ways of thinking about our physics. So And part of that is just using better words. So we have long distance color entanglement as we go towards low X. So we've already heard a little bit about the anti-shadowing, about the fact that, okay, this is a typographical error, or rather incomplete. This is supposed to be no Q bar enhancement. No anti-quarks were seen in the Drell-Yan data. Now that's very old data now. And it definitely use. Oh yeah, I know what happened. I copied this over from another talk and then didn't. Yeah, okay, so this is supposed to be Q plus Q bar. And one idea is that at short distance, okay, so we had a lot of talk about PN pairs in certain scaling range versus PP pairs, but what is the hardcore, or what is the short distance nucleon interaction? Long distance, we have a picture of meson exchange, and so we have QQ bar exchanges dominating. And so whatever is governed by sensitive to that should show up sort of equally in Q and Q bar. But there is evidence, both theory and experimental, that at short distance it's really QQ interchange with a gluon balancing color. And so that gives a very different dynamics of the quarks and the anti-quarks as probed in DIS. And in particular, it means that in this anti-shadowing regime, fits to existing data and models suggest that there is an important gluon enhancement, perhaps stronger than the DIS.
No. It should the valence score hold. It's a type of
You're saying this should be Q minus Q bar. No, but
Q minus Q bar.
Well, DIS measures Q plus Q bar, and it sees an enhancement. Now, it may be that the enhancement
separately from Drell-Yan, that anti-quarks are not enhanced but suppressed.
Yes, this was supposed to be Q bar. I'm sorry. Bar has disappeared.
But that means that you have to previous line to write Q valence.
Oh, yeah.
No, well.
That's 2Q. Okay. So
I mean, the DIS measures Q plus Q bar, and it sees an enhancement. Now, the interpretation is, yes, that the Q valence is enhanced, and but the quarks are enhanced, and the anti-quarks are not.
Well,
Yeah,
but you cannot. Okay, fine.
I will not say that the data on the Drell-Yan are very conclusive on that, because the enhancement you're looking for is like 4 or 5%, and I don't believe they have normalization.
Well, but it's negative.
Well, okay, but so I will show the modern analysis, and you can decide.
Modern analysis maybe say something.
So this is a very recent analysis of a very wide range of data. So this is carbon and lead, modest Q squared and large Q squared. So they have every possible species. They have here the valence up quark. I just pulled out of that the valence up quarks, the anti-quarks, and the glue. So I would say that their fit certainly allows for an anti-shadow. So the whole EMC effect in these log plots, of course, is jammed into a corner where you can't see it. So with this is the no or hen plot. But so the anti-shadowing region, yes, the fits are compatible, that there's anti-shadowing in the anti-quarks, but the error bands, let's say, have no preference. Whereas here there's, in the quarks, in the valence quarks, and in the gluons, there's a strong preference for anti-shadowing, for enhancement of gluons in this region.
Well, for the gluons, it's compatible with zero.
For gluons, we don't know.
With one, sorry.
Wow. There is no experimental data for gluons.
Well, that's why that's why we want to shrink these error bars with the EIC. Okay, so how can we shrink those error bars with the EIC? So we can do EA to open charm. And so this is the basic diagram that we expect to dominate. And then, of course, we have an issue that we don't detect charm quarks directly, but if we can tag the presence of a D or a D bar, we have a high confidence that is well quantified that we are, in fact, probing this photon-gluon fusion diagram. It also means that the gluon momentum fraction is not the Bjorkane X. It's shifted by a term that's mostly due to the charm mass. So this is two curves, x of 0.1 to the solid line, q squared of 10, x of 0.2, Bjorkane x of 0.2, q squared of 10, Jeb squared. And this is the x prime, the gluon momentum fraction. So it's shifted from 0.1 to about 0.3 or from 0.2 to about 0.5, but it's still very localized. So you can very much measure the gluon momentum fraction. The isolation of the D meson is a combination of particle ID, looking at the kaon decay channels, and the vertex reconstruction. So this is the vertex. This is suppressed, and this is in microns, I guess. And so this is the resolution that we expect from the high precision vertex tracker. This is Julia's work mostly. So by putting a cut here, we can eliminate all the prompt kaons and all this tail are D mesons. So this is sort of a blow up of the previous plot. The green line is the current understanding, and so this is just the ratio of possible values of the gluon distribution in the nucleus divided by the central value of one of the particular fits. So everything is normally around 1. It doesn't say 1 doesn't mean that there's an effect or not an effect.
What are these red lines?
So this is the Monte Carlo approach that you generate, you take the data, you generate pseudo data, and you generate fits, and then this is ensembles of fits.
It's a rewin with Monte Carlo.
So the green speckle is our current understanding or current ignorance, and the blue lines are the projections of what we can do with the EIC. With the 100 inverse femtobarns, which is optimistically a year of running. So one has to think about how many years of running you
Why
have
do
on
you
each.
need all this chart? We have a good study that is dominated by systematics down to 2, 3, 4, 5. The first study that actually shows that all this is feasible. It's also showing that you don't need to understand. Actually, it's like a year 1 physics. This is a great stuff that you can do.
I think because this study was focusing on high X.
High X.
I mean,
And the cross section
0.05 and up.
rapidly when you go to the high X.
But still look out the systematic errors are which, right?
All right.
Then
And
once
you
you
Might
reach them,
errors, yeah.
it doesn't matter how much you
10%.
measure, you're not getting any better, right?
But the further to the high X you go,
unless you go to X
the
0.8
difficult
or something like that. But here, all this region that we are showing.
No, the 0.8, there's no statistics, even at this level.
All right. So
Well, these are a few
I will show
percent. I mean,
something
this is a couple percent
because it's
errors.
So we completely disagree on this. And at least we agree on the result, and we completely disagree on the statistics.
So this was a 10 to 20%.
we assume
That's a charm we used with the tagging, like on displaced vertex.
We assume 10 and rows.
Maybe that is best
Oh,
done
okay, I need to.
you and Julia's talk, right?
Okay,
Go on.
okay. Okay, so going significantly below that anti-shadowing region into the shadowing region, now we're probing coherently over a distance that's larger than we think of as the size of the nucleon. Either if you think of the photon as materializing as a colored dipole, QQ bar pair, that then one parton, one quark, the quark interacts with one nucleon and the anti-quark interacts with the next, the different nucleon behind it, or there is some color correlation. We talk about color van der Waals forces, so there could be some long distance color correlation between, or color entanglement between some the state in here and the state in here, color polarized. And so the idea of gluon fluctuations that are larger in size than the nucleon seems very strange, but that's because our notion of the size essentially comes from probes that can't disentangle, low energy probes, so it can't disentangle such fluctuations from the fluctuations of the vacuum. So here's the vacuum that we all know and love. And these effects are fundamentally no different than saturation, or especially saturation as we want to view it in nuclei, because we have to build up the gluon density from multiple nucleons in a longitudinal slice to the nucleus. And we also know that as you go down lower and lower in X, there's a diffusion that causes the gluon density to spread. So if we're looking at the gluon generalized parton distribution of the entire nucleus, we know there are effects that just come from sort of the first order dynamics that we need to study carefully to be able to see any real transition to saturation. Okay, so talking about tagging and reconstructing the nuclear final state, and although there's fascinating things to be done in heavy nuclei, I'm going to mostly focus on the light nuclei and explicitly on the deuteron, but the nature of the electron ion collider allows us to look at a variety of light nuclei, including with polarization. So we have a deuteron with some kind of a wave function which says that there's a neutron and a proton, and we detect a proton momentum, and we can resolve the proton momentum in light cone variables. So alpha is the longitudinal light cone momentum fraction, and there's a 2-vector P transverse, P perp. And all the fragments add up to the total momentum of the nucleus, and all the transverse momenta add up to 0. So if we tag, so of course so the idea of course is that this momentum effectively, or this minus that, both of which are measured, measures this. Of course, if there are final state interactions between here and here, or between this and this, then that distorts the picture, and that's part of the story of why we want to do this and what we need to do it with precision. So using a lot momentum fraction allows you to deal with this in any kinematics of a collider or a fixed target, but if you boost back to the reference to the deuteron rest frame or your nuclear rest frame, then alpha minus 1 is basically the momentum of the initial particle in the ground state divided by the mass. So in a heavy nucleus, the Fermi gas would be up to about 0.25, 0.27. In the deuteron, it's not quite right to talk about Fermi momentum, but values of 0.1 are large for the deuteron. But so there's several essential things about the electron ion collider for this physics. One is that everything is boosted forward. So a zero momentum particle in the rest frame is now boosted by 40 or 50 GeV over C, or boosted to 40 or 50 GeV over C, depending on what, depending on what collision energy. So it's very possible, it's very straightforward to tag either spectator protons or spectator neutrons, because hadron calorimeter will measure a neutron with essentially 100% efficiency. And it can get very good angular resolution on the neutron. So compared to measuring neutrons in a fixed target experiment, this is almost easy. And the problem in a fixed target experiment is getting the protons, the low momentum protons, out. So alpha equals 1 would be a zero momentum proton. That's sort of the perfect place to look for the simple one-body dynamics of the nucleus. And those protons never make it out of a fixed target. So the best we can do is 70 MeV over C with a specialized low luminosity, not so low luminosity. That's why we have bonus 12 and alert. Bonus 12 is an improvement of luminosity over the previous, and alert is yet another improvement. But neither, certainly not bonus 12, will not reach the luminosity of class 12 by itself. The class 12 can only get to the minimum value of class 12 is 0.2 with no supplementary vertex detector. And the other thing is polarization. Well, we can do polarization in class and in other experiments in other halls, especially longitudinal polarization. But that introduces even more material, and it reduces the acceptance. And transverse polarization, I would say we have ideas. Some of the ideas are graced by the PAC, but we haven't proved any that we know how to make them work. Or even if, or to the extent that we know how well they work, it's enormous challenges with combining luminosity and acceptance. So the transverse polarization, again, comes along without any penalty. There's no surrounding material in the EIC, in the collider. The ions are in vacuum. So it's really a great leap forward in terms of doing this kind of physics. Okay, so here is a quantitative discussion. This is how, so this is simulation. So this is the T prime is how far off shell the neutron is based on naive spectator kinematics. So the on shell point is at 0, and fundamental theorem proves that if you can extrapolate perfectly to the on shell point, you get exactly the free neutron structure function. Of course, that extrapolation does not have to follow this simple curve that we've drawn, because final state interactions can cause effects all the way down to the physical threshold, which is this dashed line, which is defined by the binding energy of the deuteron. But again, we have a great deal of understanding of final state interactions at these low momentum. We know how to explore kinematic domains where they're predicted to be very small versus kinematic domains where they're expected to be large. So this is an extrapolation for alpha less than 0.02, and this is basically the p-perp variable of the proton simulation going all the way down, and many systematic errors are included in these error bars. And then this is just one rather small bin in Q squared, and an illustration of the extraction, the on-shell extrapolation of the on-shell neutron structure function. Okay, so now, again, talking about the EMC effect in the deuteron. I mean, the true EMC effect is supposed to be the ratio of the deep elastic scattering on a nucleus to the incoherent sum of deep elastic scattering on a proton plus a neutron. But we don't have that, so we instead divide by the deuteron. But it's clear in our minds that the deuteron is bound, and there's a neutron and proton are interacting at least some of the time, so there is an EMC effect on the deuteron if you define it to be the ratio of the deuteron to the neutron plus proton. So how do we use this to measure it? So the dashed line would be a representation of the measurement that you make at very small alpha, alpha very close to 1. And so it goes all the way down to about here, and then you extrapolate to the on-shell. So this is an experimentally determined on-shell point from the previous slide. And now, instead of looking for alpha close to 1, you look for alpha large, 1 minus alpha large, so greater than 0.2, for example. Now that pushes you far away from, your kinematic limit now is much farther away from the on-shell point, so you have farther to extrapolate. But if high momentum nucleons in the deuteron had no EMC effect, then you expect the data to follow the same line that you measured for alpha very close to 1. If there's an EMC effect, and this is just a particular model, this was part of an LDRD at JLab a few years ago, then we expect the data to lie here and extrapolate to the best that we can to be consistent, let's say, in their extrapolation to the same on-shell point. So this discrepancy is the measure, direct measure, nearly direct measure of the EMC effect on the deuteron. So we can, it doesn't really matter. And you probably, I mean, when Christian Weiss did the model, it's probably consistent with something you've done.
Still a model.
It's still a model. I mean, how big this is a model. The size of this error bar. So you can say, well, the error bar tells us with what precision we can say that there is or is not an EMC effect in the deuteron.
But this would by itself give you measurement of the EMC effect. In particular, say you may get effect due to final state interactions, which will destroy spectator measurements. That's on the same scale. In principle, maybe not.
So, but we know how. So first of all, we can include that, and second of all, so this is integrated over all angles. So Ulrich showed us how in the NP system, relative to the momentum, if you look at the center of mass angle of the proton relative to the NP total momentum, there's a very strong final state interaction effect around 70 degrees. It moves around a little bit according to momentum, but in either the forward or the backward direction, it's very, very small.
It's a different story. This is a different high energy final state interaction, which may originate from just the fact that you produce heat, say neutron produced hadrons in the end, which go forward, they may hit the proton and distort it from momentum distribution. That's actually what we also discussed this case.
That's right, that's right. And when goes, yeah, so that is certainly something that has to be explored. One way that we can look at that is this middle point. So the data here was, this was measuring a spectator proton and then inferring the nearly on-shell neutron, active neutron. But we can also measure a spectator neutron. And with a state-of-the-art hadronic calorimeter, between 30 and 40% over root E energy resolution. That's 4 to 5% momentum resolution at 50 GeV neutrons. So that corresponds to measuring alpha to a precision of 0.04, or the rest frame momentum of the active proton and the deuteron to a precision of 40 MeV over C, which is much better than anything like that has been done before. So then we can essentially measure the on-shell structure function of the proton as it's bound in the deuteron, and so we can calibrate a lot of these issues by doing both tagging the spectator proton and tagging the spectator neutron.
Yeah, but it doesn't solve the problem, because yes, you will see some deviations, let's say for the proton or for the neutron, and you a priori it's not excluded that you can, but if you do just generically, final state interaction will be difficult to exclude from interpretation. And what is important, that final state interaction effects is not small. That's exactly the same issue that extrapolation goes to the book. The scatterings don't have enough singularities to avoid basically damp. So from this angle, you cannot distinguish final state interaction. Other ways, and well, I hope the AICs gel up with doing things, there should be separate ways we tell the problem despite of what happens in terms of final state interaction for the slow particles. That's the main thing. We know more or less now what happens with the fast particles, but slow we don't. That's the problem.
Okay, so I'll say we have 10 years to figure out, improve our understanding of how to handle these challenges. Polarization, of course, is very important. So longitudinal polarization gives rise to, allows us to measure G1N with high precision, subject to, well, I think the final state interaction effects are much easier to handle when we're doing the extrapolation very close to alpha equals 1, alpha spectator. This is alpha S, alpha strong, not alpha spectator. And so, of course, having high quality extrapolations to the on-shell neutron allows us to do flavor analysis, allows us to improve the precision of the Bjorkane sum rule, makes contributions to delta G, and the effective coupling constant, alpha S, can be measured both in the low and the high Q² range in this way. I used to put AD² on here for Alexander Durr, who did one of the analyses, early analyses to extract the effective alpha S at low Q², and Abhay Deshpande is very interested in the high Q² precision measurement of alpha S at high Q². Okay, so I can get rid of all of, well, I'll never get rid of all of Mark's objections, but I can counter. I can say, if you don't like,
it's warnings.
Point taken. So I can go one better, knowing that I have this problem. So then I can look at double tagging, or diffractive DIS. So in diffraction, you have some scalar, isoscalar exchange, which is not necessarily perturbative. I mean, it could be a gluon ladder, but it could be a perturbative gluon ladder, but it can be something non-perturbative. And then you do deep inelastic scattering on that. But the thing that's important in thinking about incoherent diffraction on a nucleus is that this system, this hadronic final state, is created small and it's created color neutral. In deep elastic scattering, you have a current jet and you have the target fragmentation region, but they have color by definition, and so there's a whole connection between them, of which a huge amount of modeling is being done at the LHC, and it's quite impressive. And so in general DIS, these two regions are connected, but here in diffractive DIS, they're not. So there's no final state interaction between this stuff and this stuff, in principle, because you're creating this in a small color singlet. So the only interactions you have are the ordinary low energy NNT matrix. So then, can we use this as a probe of the quark-gluon structure of that T matrix? So if you're measuring at low relative momentum between the proton and the neutron, then you're essentially, by all the same arguments, it's just coherently scattering. You scatter off of a free neutron, almost free neutron, or this connects to an almost free proton. And all of that is calculable from EP DIS, or EP diffractive DIS, because to the extent that this is purely isoscalar, it's exactly the same on the proton and neutron. Now, on the other hand, at high PT, in the proton, high meaning high on the scale of the deuteron momentum, or
what is the deep purple talking about? Which particle? The final peak?
So this is your paper. I'm coming to your paper, but so it's the relative momentum. It's the p perp of this proton relative to the average of the two, or equivalently up to longitudinal momentum fraction corrections. It's the mass of this empty system. So when the mass is large on the scale of the deuteron mass, I mean the deuteron binding, or PT is a few hundred MeV over C rather than, then you're confining, you're to a large extent constraining this to be in a short distance interaction, and therefore this is seeing something which is not just the incoherent sum of two nucleons, but it's seeing the nucleons as they're close together. So this is starting to probe more directly the quark-gluon dynamics of a small object of two or more nucleons. And so probably the most quantitative example would be, and again, it doesn't have to be the deuteron, but deep virtual, let's say, I'm not quite sure, all the adjectives sort of get lost because everybody ends up having different definitions, but electron, deuteron, scattering at high Q squared, going to a proton-neutron final state and some defined mesonic state. And the simplest case would be either vector meson or a photon. And in fact, experimentally, the simplest case is probably either the phi or the J psi, because you have charged particle channel, I mean, in the row as well. So if you do, I'm just for being specific, talk about phi production, you measure it in the K plus K minus channel, and so you have only one neutral particle in the final state, which is an enormous experimental advantage, especially for fixed target measurements. But of course, okay, at the EAC, we can measure that neutron with pretty good precision. Okay, so in this paper, there's a much prettier, much more quantitative diagram. So here's the basic idea. You're doing deep virtual phi production. The transition from gamma to phi is dominated by the gluon diagram, even at relatively large X and relatively modest Q squared. That was explored in some detail in very nice papers of Peter Kroll and Sergei Skokov. And then if we're looking at large mass large PT, large meaning like hundreds of MeV over T, then essentially the deuteron wave function is being resolved to a short distance configuration of the neutron-proton pair. And so we're measuring some sort of transition, GPD in the continuum, and I shudder to think about all the possible spin angular momentum structures that are there, but let's just sort of sweep that under the rug. I guess that's why, Jerry, this paper is 60 pages long. But so we can probe, we can look at the gluonic structure of those interacting. Well, if you want to measure the spatial distribution, you have to measure a transverse momentum distribution of phi. In addition, so that's the momentum transfer. I mean, okay, you have to decide what's your favorite light cone orientation, but so the p perp of the phi and the p perp of the proton are with respect to several different variables and are both important. The mass, so if you want, you can, instead of talking about p perp here, we're talking about the mass. We want to measure the distribution as a function of the mass of the p-n pair, and we want to measure the distribution as a function of the p perp of phi.
Maybe it's a question for Jerry or Mark. If I would change the electron to a gamma, yeah, let's say I do it a GluX.
Well, then you want to do it with a J psi in order to get a hard scale. And okay, GluX has a slightly, it has to, I mean, the best way to do that would then be untagged and crank up the luminosity, because at 9 GeV, you're infinitesimally above above threshold.
But I have to have a J psi. I can't do it with any of the light elements.
Well, then it's not perturbative. Then you've got sort of all the Pomeron kind of whatever.
So interpretation becomes.
It doesn't mean you shouldn't do it, but
also I'm a bit confused. I thought that also PT for proton and neutron, few GeV, not few hundred MeV. Right. Because we know that PN or PP scattering, say up to 1 GeV energy, is also for all kinemats.
Mark, you know, you always want Q score infinity. We end up doing Q score of 2. And
no, not talking about Q square. He's talking about how big the curve has to be to constrain this to be a small size.
Interesting reaction anyway. Well, for different kinemats, we have different dynamics.
Yeah, 100 MeV, it's not enough.
So, okay, so if you increase this up to GeV scale, you do a much better job of constraining this to be a small configuration. But you also, that comes at a price. You pay 2 penalties. One is count rate, and the other is that the minimum momentum transfer gets larger. And that always, people are always worried about understanding exactly what this mechanism is when you have a large momentum transfer.
Well, otherwise, you don't have Hard interactions all the way.
No, the Hard interaction is the value of the Q squared. That's a separate question. And the higher the Q squared, the Q squared doesn't.
Basic computing mechanism would be longer, in which I can, without moving pollutants at short distances, just putting them in the same impact parameter. So keep one proton one way and neutron another way. Have large transverse momentum from strong interaction.
So the angular dependence as well as the magnetic modulus of P perp should help us just understand those effects. But yes, I agree.
And if I would follow some logic, I got once I have Chekhov type model, I would have very different mechanism. I would attach two gluons to J psi, and then split it into 2 phonorons, one attached to one neutron, another to another. That syntax is once again right. So
well, I mean,
options.
we will There is data has been acquired. It was preliminary results were presented last week in Hawaii on deep phi production on the proton. So we are moving forward to having a better understanding in the modest kinematics of EIC0 of Jefferson Lab to 12 GeV as to how well we understand phi production. And we will have comparable data on the deuteron in a year. So I have a student who I have hidden all these horrible difficulties from so that he will remain enthusiastic about trying to explore this reaction. That's cool. This reaction at JLab, but clearly we could go, yes, you really want high Q squared, you really want to be able to go up to GeV scale in this relative momentum.
If you have data on phi, it would be really, there's a puzzle from 5 trillion data, which seems to indicate that phi rescatters on the nucleon is cross-section much larger than what we expect.
Well, are you talking about photo production data? I mean, well, I want to kill that with high Q squared.
Even more interesting.
And okay, there is certainly data, and there's a discussion by Kroll and Goldsborkov about corrections at this vertex, but there is still the Hera data strongly suggests that there is a separation between the hard part and the soft part at Q squareds at 10 Gev squared and below.
You know, independent of all GPDs and what Jerry's work, this process must be something, you know, you're dripping your mouth in. I mean, this is, you measure the phi or the J psi or whatever. You only have to measure the proton or the neutron because the kinematic of the process totally determines.
Yeah. You measure
over a total range of Q squared G, what God do you know? You can measure this thing to death. This must give you every possible information you want about the short-range correlation.
Actually, you should have
Just in principle terms, without being too specific, this is a key process for what you try to do.
Okay, I'll tell that to Mitch.
On the top of that,
Every time we read one of your papers.
Yeah, but then you go with higher T, like the incoherent dominates, right?
Well, no, if the detector can detect the deuterium, especially if you start with polarized deuterium, piece of cake. You start to separate the scattering from S wave, D wave.
I think this is kind of a classical considered situation. In 2019, this will be done. We're working very hard on one group B, and it will be very borderline kinematic. So we'll study something, but some things will be hard to interpret. And moving on with an EIC, we'll be able to do it superbly well.
You have a deuterium.
Yeah,
It's touchy.
beautiful.
It goes apart. I mean, you can measure the depth.
2020, 2021, we'll do it on a longitudinally polarized.
Charles, your time is up.
Yes. So's my talk. Okay. Everything's on that slide I've said, so.
Actually, I'm surprised that to do polarized white nucleon in the list, we should go to short-range correlations with polarized neutron, which is probably more major thing for measurement of SCD wave.
I think there is
It's not
finally.
tensor polarized.
There is finally, yeah, okay, so tensor polarized deuteron is a beautiful thing to do.
It's not that.
I think it's experimentally challenged.
Oh, then you will do what I think Doug did years ago, spin transfer.
Yeah, in all B, these things, it's not tensor polarized, and it's whole B, so you don't have a polarimeter that you can.
I think the EIC can do tensor polarization as well as it can do longitudinal polarization.
Yeah.
Another important point. We will do like some experiments on polarized lithium, at the very least the EMC type measurement, which was scoffed at decades ago. Now finally people are intelligent enough and liberal-minded enough to say, yeah, we should do that. And we can do lithium, polarized lithium-7, probably no fundamental challenge in the EIC. Polarized lithium-6 is the same challenges as polarized deuterium. So it's definitely...
Lithium-7 is better from polarization, from EMC.
Yes, lithium-6 you can do the tensor polarization, and so if you're excited by that, but so I'm not favoring one or the other. I'm just saying they're both in the mix.
Are there any questions? Yeah, I have one. Your first slide, you said that the nucleon short distance interaction comes from the exchange of two quarks and a gluon.
Possibly.
Okay, where does that come from? Whose idea is that? Is that your? I mean, I never heard of that. So
I think I'm inspired a bit by some Isak Sargsyan. I'm also you have the overlap of
what do you mean quark anti-quark and a gluon?
No. I mean quark. I mean
You can't do it. You start out with 3, give up 2, you have 1. So
Well, I think
no, you interchange a quark from each one, and you balance color with the gluon.
that's standard.
Okay, anything else?
It's only the group.
Charles, thank you. So then we meet at 2:30. It's in this.
yes, a discussion room next door. You have to.
Do we all fit in there?
Yeah, it's a very small room.
It's a small.
Well, we'll be forced to rub elbows.
Okay.
Just no sharp elbows allowed.
Think about good
Well,
questions.
the INT doesn't have this room reserved in the afternoon. Chances are it'll be open, but on Monday, but I'm not sure.
Okay.
But it's been working well over there, even though it's crowded.
You said we achieved 21, so maybe it will be okay. 9.
You just came.
Or do you want your remote device? Or is this yours?
Unfortunately,
Yeah, it's his.
Yeah, this is mine.
So you have a receiver there? Or?
Yeah.
That's
Yeah, it was a nice.